Okay, in this video we are going to prove a sufficient condition for a connected simple graph to have a Hamiltonian cycle, and the statement reads as follows. Okay, the theorem is due to Dirac, and the statement is as follows: if G is a simple graph with n vertices where n greater than or equal to 3 and the degree of each vertex is greater than or equal to n by 2, where n is the number of vertices in the graph, then G is Hamiltonian. Okay, so this statement is it's only a sufficient it gives a sufficient condition for a connected simple graph to have Hamilton cycle. Okay, it only gives a sufficient condition. Okay, so it doesn't say anything about the necessary condition for a particular graph to have a Hamilton cycle. Okay, so do not give, it do not provide a necessary condition for the existence of a Hamilton cycle in a graph. Okay, it only gives a sufficient condition, but it do not provide a necessary condition for the existence of Hamilton cycle. Okay, for example, if you look at C6, a cycle on 6 vertices. Okay, C6, a cycle on 6 vertices. Okay, in this case we can see that in C6 number of vertices is 6 and the number of edges is 6. Okay, and the degree of each vertex is 2. Okay, since it is a cycle, so C6 will look something like 1 2 3 4 5 1 2 3 4 5 6. Okay, so this is what C6 is. So here we have 1 2 3 4 5 okay, 1 2 3 4 5 okay, 6 vertices and 6 edges, and if you look into the degree of each vertex, you can see that the degree is 2. Okay, 2 here, 2 here, okay, 2 here, etc., etc. Okay, so here this C6 it is a Hamiltonian graph. Okay, C6 contains all the vertices, all the 6 vertices, and it is a cycle, and the vertex each vertex appear exactly once. So C6 is a Hamiltonian graph, and here again we can see that okay, if you look into C6, okay, it violates the hypothesis of the statement. Okay, degree of each vertex here is 2, and here if you look into this condition, okay, n by 2 condition, n by 2, n is 6, right? Okay, that is 6 by 2, which is equal to 3. Okay, and here we can see that okay, 2 is strictly less than 3. Okay, so that violates this condition. Okay, so that says okay, there are Hamiltonian graph okay, that do not satisfy this condition. Okay, and one example is this C6. Okay, again we can see that there are infinitely many C7, C8, etc., etc., and you could also find many other graphs. Okay, so it only gives a sufficient condition that says okay, if a graph is a Hamiltonian graph, and okay, and if all the vertices satisfy this condition, definitely okay, that graph is going to be Hamiltonian. But there are graphs that do not satisfy the hypothesis of the statement that has Hamiltonian cycle. Okay, so it only gives a sufficient condition. It doesn't provide a necessary condition for the existence of a Hamiltonian Hamilton cycle. Okay, so let's go and prove this statement. Okay, so we are going to prove this by contradiction. Okay, so we assume something the contradictory for the statement, and we arrive at a contradiction, and that says the assumption is wrong. Okay, let's see how that proof by contradiction can be applied to prove this statement. Okay, so suppose that the statement is false. Okay, and that says, okay, for some n greater than or equal to 3, there is a non-Hamiltonian there is a non-Hamiltonian graph. Okay, let's call that graph H. Okay, which satisfy the hypothesis. Okay, with degree of all vertices in H is greater than or equal to n by 2. Okay, for every vertex of okay. So we are going to assume that the statement is false, and for some n greater than or equal to 3 there is a non-Hamiltonian graph. Let's call that H with the degree of each vertex in that graph is greater than or equal to n by 2. Okay, and here we can see that this graph H is connected. Okay, first note that G is connected. Okay, so that's very easy to see here. This graph H is connected. Okay, because of this condition, degree of each vertex in H is greater than or equal to n by 2. Okay, first note that H is connected. Okay, so if H is not, if H is not connected, then what is going to happen is that if you look at the component that have less number of vertices, then all the vertices have degree less than or equal to n by 2 minus 1. Okay, so that will violate this condition of the hypothesis. Okay, so because of a reason the H is connected. Okay, otherwise what is going to happen is that okay, we look into the smaller component. A smaller component has all the vertices of degree, all vertices have degree okay, at most n by 2 okay, n by 2 minus 1. Okay, so if it is not connected, then that is going to happen. Okay, and that violates the hypothesis. So we can assume that H is connected. Okay, so let's go and prove this statement by using this graph H. Okay, so what we are going to do is we are going to take that H and we are going to add more edges into that graph H. Okay, so we are going to build a super graph using this H. Okay, so add more edges into H until we get a maximal non-Hamiltonian graph. Okay, so we are going to add more edges into H until we get a maximal non-Hamiltonian graph. Okay, so let's call this modified graph G. Okay, and here again we can see that okay, G by construction, okay, we added more edges into H until we get a maximal non-Hamiltonian graph. It's a non-Hamiltonian graph. That means if you add one more edge, then G will become a Hamiltonian graph. Okay, and again we can see that the degree of each vertex in G is also greater than or equal to n by 2. Okay, because this graph H, okay, is chosen in such a way that the degree of each vertex is n by 2. So here we added more edges, so it will only increase the degree of each vertex. Okay, and still we can see that the degree of each vertex here is greater than or equal to n by 2. And also here we started with this connected graph, and that says okay, G is also connected. Okay, so let me write that down. So okay, in G we can see that the degree of each vertex, okay, in G is also greater than or equal to n by 2. Okay, for every vertex of G, and also okay, G is connected. Okay, next what we are going to do is we are going to use this G to get a contradiction. Okay, so using G we are going to get a contradiction. Okay, so we know K n, okay, is Hamiltonian. Okay, so K is Hamiltonian, and since K is Hamiltonian, okay, we know that this K n is not equal to, or G is not equal to K n. Okay, so K n is the complete graph on vertices. Surely that is Hamiltonian, and okay, here G is constructed in such a way that okay, G is a maximal non-Hamiltonian graph. Okay, and because of that, right, that we can see that G is not equal to complete graph on n vertices. Okay, and since G is not equal to n, okay, we can always find two non-adjacent vertices in G. Okay, so therefore in G there are two non-adjacent vertices. Okay, since G is not equal to K, okay, there are two non-adjacent vertices. Okay, and let's call those vertices say U and V. Okay, and next what we are going to do is okay, we are going to take that graph G, maximal non-Hamiltonian graph, okay, and we are going to add this edge UV. Okay, so remember these vertices are non-adjacent, so they are not connected by an edge, and okay, G is a maximal non-Hamiltonian graph. So if you add one more edge, then immediately this graph will become Hamiltonian. Okay, so let G plus UV, okay, it means we are taking this graph and we are going to add the edge UV into the graph. Okay, so let G, okay, G plus UV be the super graph obtained by adding an edge between u and v. Okay, and here again we can see that, okay, since, okay, G is maximal non-Hamiltonian, okay, since G is maximal non-Hamiltonian, okay, G plus UV, okay, adding an edge between two non-adjacent vertices will make that graph Hamiltonian. Okay, so G plus UV is Hamiltonian. Okay, so since G plus UV is Hamiltonian, it has a Hamilton cycle. Okay, and let's call that Hamilton cycle C. Okay, so let's C be a Hamilton cycle in G plus UV. Okay, and okay, here we can see that, okay, if you look into, okay, this cycle, Hamilton cycle, okay, this Hamilton cycle, it will contain this edge UV. Okay, so let me write down here. So here we can see that if you look into this Hamilton cycle, so C contains the newly added edge. Okay, it contains the edge UV. So otherwise what is going to happen is that, okay, otherwise C is going to be a Hamilton cycle in our graph G. Okay, so we constructed G in such a way that that is a non-Hamilton graph. Okay, maximal non-Hamilton graph. Okay, so that says C contains the edge UV. Otherwise, okay, C is a Hamilton cycle of G. Okay, so that is not possible. Okay, so let's call let's call this cycle, or let the cycle be like, okay, you started from this U, okay, this vertex, and let that be equal to V1, V2, V3, etc. Vn minus 1, Vn. So let Vn be equal to, so we started with the graph having n vertices. Okay, so Hamilton cycle will have those n vertices. Okay, so let that Hamilton cycle be V1, V2 up to Vn, and assuming that U equal to V1 and Vn is equal to V, and since this is a cycle, then okay, we have U here. Okay, so the initial vertex and the final vertex is the same since it is a cycle. Okay, so let that cycle be this one, and suppose the cycle is denoted like this. So we have this cycle, and this cycle have these vertices V1, V2, V3, and here, okay, this is a Hamilton cycle in our graph. Okay, G plus UV. So we started from here, U equal to V1. Okay, V1. So this is V2, V3. Okay, V4. Okay, similarly this will also be equal to V2, V3, V4, etc. Okay, and it goes something like this, and Vn minus 1 and Vn, which is equal to V and the final edge. Okay, so next what I am going to do is I am going to define two sets, okay, using this cycle, and okay, let's call the first set S, and this set S is defined as follows. it is going to be all vertices element of which belongs to this cycle C. Such that there is an edge from this vertex u, the start vertex u, to v I plus 1 in or modified graph G. Okay. Okay, so it contains all the vertices belonging to this cycle, in such a way that there is an edge from u, this vertex, to vi plus 1 in the graph. For example, in this case, if there is an edge from this, say, vi, v1, which is u, to k. So in that case, vk minus 1 will be an element of S. And similarly, if there is an edge between vi and say vk plus 2, v1 and vk plus 2, then vk plus 1, it belongs to this one. It says something like this. You have this cycle, and suppose that this is our vertex u, which is equal to v1, and if there is an edge from u to, suppose that this is, say, vi plus 1 and this is vi, and there is an suppose that there is an edge here in C, and if there is an edge between this vertex u and vi plus 1, if that is the case, then we add this vertex vi to this set S. So this is how we define this set S, and let's define one more set. I think it is very clear, right? I will say that once more. It says something like this. Consider this cycle C, and suppose that there is an edge. Anyway, there is an edge from vi to vi plus 1, and suppose that this is our starting vertex v1, and and this set is built as follows. So if there is an edge between this vertex u, which is equal to v1 and vi plus 1, if that's the case, then we add this vertex vi to this set S. If this is the case, then vi it belongs to S. And we define one more set. Let's call that set T. So it is going to be all vertices belonging to this cycle C, such that there is an edge from there is an edge from here we are going to consider this vertex from V to Vj in G. So if there is a direct edge from this V, which is equal to Vn, to any vertex in this cycle, then we will add that vertex to this set. So for example, if there is an edge between, say, say V and say Vk plus 2, in that case what we do is we will add Vk plus 2 to T. So it's a very simple rule. These two sets are built in this way. So S is going to contain all the vertices element of this cycle, vertices belonging to this cycle, such that there is an edge from u to vi plus 1 in G, something like this. And this T, it is going to contain all the vertices Vj belonging to C, such that there is an edge from V to Vj in G. So here we can see one important thing here. So if you look into these two sets, we have some good property here. Let's see what that property is. So if you look into this Vn, then we can see that the last vertex, that Vn, it doesn't belong to T, because here we are dealing with a simple graph, so there won't be any loop or parallel edges. So then we can see that Vn it does not belong to T. Why? Because by definition, if V of n belongs to T, it means that there is an edge from V, which happen to be Vn to Vn. So we will have a loop in our original graph G. So we assume that G is simple graph, then that is not possible. And that says Vn it doesn't belong to T. So since otherwise we will have a loop. Since otherwise there is an edge from V to Vn, and Vn is nothing but V, and that is a loop, which is not possible. And also we can see that this Vn, it is also not an element of S. So if you look into this particular thing, if Vn belongs to S, we can choose V1 to be equal to Vi plus 1, right? Let's see what is going to happen. So in this case, what we can do is we can take this Vn plus 1 to be equal to V1, and same kind of reasoning, since otherwise what is going to happen is that again we get a loop. We will get a loop from u to V1, which is equal to u. So if Vn belongs to S, it means if this belongs to if Vn belongs to S, it means there will be an edge between V1 to V1 or u to V1, and V1 is nothing but u. In that case also we will have a loop here, and since this graph G is assumed to be a simple graph, then such a situation it won't occur. That is not possible. And that also says this Vn, this vertex Vn, it doesn't belong to S as well. So Vn it doesn't belong to T, and it doesn't belong to S. And therefore it doesn't belong to the union of S and T. Therefore we can say that this vertex Vn it doesn't belong to S union T. And that says, so here we build this S and T by using the vertices in this cycle, and this cycle corresponds to a Hamiltonian cycle, and all the vertices will appear in this cycle, right. And that says if we take the union of S and D, the cardinality of that union set will be strictly less than n, because V n, okay, doesn't belong to this T and S, okay. And that says we take the cardinality of S union T, the cardinality is strictly less than n, okay. And again, okay, we can also see one important thing. Okay, also we can see that for every edge incident with U, okay, so it is something like this. Okay, for every edge incident with U, okay. So anyway, we can see that if we consider this cycle, that is a Hamiltonian cycle, and all the vertices appear in this one, right. And if we consider all the vertices incident with V1, okay, then another vertex okay, which satisfies this condition belongs to this set S, okay. And that says the cardinality of S, okay, it is going to be the degree of this vertex U, okay. Similarly, you can see that all the vertices adjacent to V belongs to this T, and that says the cardinality of T, okay, it is going to be the degree of this vertex V, okay. So that's what I am going to write here. Also for every edge incident with U, okay, there is one vertex Vi in S, okay. Since we are considering a cycle here, okay, and if there is an edge from U to Vi plus 1, we add Vi, okay. So for each vertex adjacent to U, okay, the Vi which is adjacent to this Vi plus 1, okay, will be in this set, okay. And that says the cardinality of S is the degree of U, and similarly you can see that the cardinality of T will be equal to the degree of V, okay. So there is one vertex Vi in S, and therefore we can see that the cardinality of that set, okay, it is nothing but degree of U in G, okay. And similarly we can also see that the cardinality of T is nothing but the degree of the vertex V in G, okay. So here we have this condition, cardinality of S union T is less than n, okay. And next what we are going to do is we are going to prove that the cardinality of S intersect T is equal to MT, okay. If you are able to prove something like this, then we know this thing, right. Cardinality of S union T is equal to cardinality of S plus cardinality of T plus cardinality of S intersect T, okay. If this is true, then we need to prove that here. So if this is true, then this is 0, okay. So we have this condition, right. Cardinality of S plus T is equal to cardinality of S union T. The cardinality of S is nothing but degree of U, and this is degree of V, and we know the cardinality of S union T is less than T. So we have the condition, degree of U plus degree of V is less than n, okay. And we assume something like this, the degree of each vertex is greater than or equal to 3, okay, and that will contradict our assumption, okay. That's what we are going to prove next, okay. So here we have this situation, okay. The cardinality of S and 3, S is the degree of U, T is the degree of V, okay. And Next, what we are going to do is we are going to prove that the cardinality of S intersect T is empty. Okay, so if you are able to prove that no vertices are common in S and T, then we are done. Okay. Okay, so let's take an arbitrary vertex V, and if we are able to prove that that vertex it doesn't belong to both S and T, then we are done. Okay. So now, okay, if a particular vertex say Vk belongs to S and T, okay, let's see what is going to happen. Okay, then that says okay, there is an edge. Okay, let's call that edge E. Okay, joining U and Vk plus 1. Okay, so if this Vk belongs to S, by definition it means what? Okay, by definition of S it says okay, there is an edge from U to Vk plus 1. Okay, so situation is something like this. Okay, there is an edge from this V1 to Vk plus 1. Okay, so there is an edge from U to Vk plus 1, and let's call that edge E. Okay, and similarly you can also see that if Vk belongs to both S and T, then an edge, okay, joining, okay, there will be an edge between this U and Vk plus 1 by the definition of S, and let's call that edge E. And we can also see that there is an edge between okay, that V and Vk by definition of T. Okay, so if a particular vertex belongs to T, that means there is an edge from V to Vj, right? Okay, so if Vk belongs to that one, then there will be an edge between this Vn, which is equal to V and Vk. Okay, our situation will be something like that, and let's call this edge F. Okay, so let me write down that. Okay, joining U and Vk plus 1 and an edge F. Okay, let's call that F joining V to Vk. Okay, so let's see what is going to happen if this is the case. Okay, so let's look at this figure. So in this case we can see that okay, if we have such a situation, okay, we can find a new cycle here, right? Okay, new cycle here which starts from here. Okay, let me use a different color for that. Okay, so we can find a new cycle. It starts here. Okay, it uses this vertex. Okay, then it moves to this vertex and it follows this path. Okay, then uses this one, uses this edge, and it will move to Vn. Okay, from here it uses this edge F. Okay, and from F it moves to Vk, then Vk minus 1, and it uses this portion of the cycle. From V4 it moved to V3 here. Okay, now we have a different cycle. Okay, let's call that cycle C dash. Okay, and we can see that this cycle, if this is the case, then this cycle corresponds to a cycle in G, but we assume that G is a maximal non-Hamiltonian cycle. Okay, so if you believe something like this, okay, if there is some vertex common to both S and T, then we can find a new cycle. In this case, this C dash, it starts here, uses this edge, and it uses this portion of the cycle, then uses this edge and uses this portion of the cycle. Okay, and it comes back to V here. Okay, and here we have this cycle C dash, which is equal to, okay, you start from here U, which is equal to V1, then uses this edge, you move to Vk plus 1, okay, then uses this portion of the cycle Vk plus 2 all the way up to V, okay, all the way up to v n minus 1 followed by v n, which is equal to v. Okay, then uses this edge and move to vk, then vk minus 1. Okay, then v3, v2, v1, okay, which is equal to u. Okay, now we have a new cycle, and here again we can see that okay, this cycle contains exactly the same vertex in our original cycle, and that cycle is a Hamilton cycle, and this is also okay, C dash is also a Hamilton cycle. Okay. Okay, so let me write what I said here. Okay, so if this is the case, okay, if Vk belongs to both S and T, there is an edge joining this and this. Okay, and that implies, okay, so if this is the case, then that implies we can find a new cycle C dash, okay, which belongs to G, that maximal non-Hamiltonian graph. Okay, and okay, that is not possible because we assume that G is a maximal non-Hamiltonian graph. Okay, okay, and this implies okay, if something like this, if Pk belongs to both S and T, then that implies that okay, we have this new cycle which starts at v1, as I said here. Okay, v1, then move to vk plus 1 using this edge. Okay, vk plus 1, then using the other portion of the cycle vk plus 2. Okay, then okay, come back to this vn. Okay, vn, then use this edge and move to vk minus 1. Okay, vk minus 1, from here move to k minus 2, v2, okay, v1. Okay, so here we have another cycle which is a Hamilton cycle. Okay, so we have this new cycle and is a Hamilton cycle. In our original graph G. Okay, and G is assumed to be a maximal non-Hamilton cycle. Okay, so which is a contradiction. As G okay, is a non-Hamiltonian graph. Okay, and that says so no vertex okay, vk is in S intersect T. Okay, so there is no common vertex that belongs to both S and T. Okay, and because of the reason we can say that okay, S intersect T is equal to null set, and that says cardinality of S intersect T is 0. Okay, and now we can see that if we take the cardinality of this set, okay, that is nothing but the cardinality of S plus cardinality of T, okay, minus, okay, I think I made a mistake here. Okay, so it is not plus, it is minus. Okay, S union T is this cardinality plus this cardinality minus the cardinality of S intersect T. Okay, so this is 0. Okay, and that says cardinality of S plus cardinality of okay, cardinality of T is equal to cardinality of S union T, and we already showed that cardinality of S union T is okay, this is strictly less than N. Okay. So, and here again we proved the cardinality of S is nothing but degree of U, and cardinality of T is degree of V. Okay. So, that says the degree of U in G plus degree of V in G is strictly less than N. Okay. And here we have this contradiction. Okay, and this contradiction happened because of this reason. So we started with something like this, right? The hypothesis of the statement says degree of each vertex is greater than or equal to n by 2. Okay, and because we started with this one, okay, degree of each vertex in G is greater than or equal to n by 2 for all U in G, and okay, if this is the case, then we consider these two vertices, again that must be satisfied, right? Then that says degree of U. Okay, so let me call this a U dash. Okay, so in order to make these two things different, okay, for all U dash in G. Okay, and that says the degree of U is greater than, okay, if we take this sum, degree of V in G, okay, which is greater than or equal to, so this is greater than or equal to n by 2, and this is greater than or equal to n by 2. So this sum is greater than or equal to n by 2 plus n by 2, which is equal to n. Okay. So this condition says the degree of U in G plus degree of V in G is greater than or equal to n, and here we arrived at this conclusion. So okay, if you assume that the statement were false, okay, statement is false, okay, degree of U in G plus degree of V is less than n. Okay, so that's why we got this contradiction. Okay, and that says our assumption was wrong. Okay, so it all started from this thing, right? Okay, suppose that the statement is false, and we assume that there is a non-Hamiltonian graph H with the degree of each vertex is greater than n by 2. Okay, so this is false, and that says if this is satisfied for every vertex in the graph, then the graph is Hamiltonian. Okay, so and that's it. That's the proof. Okay, it's a very nice proof. Okay, so in the next video we will see another sufficient condition for a graph to have a Hamiltonian cycle.